A particle with a charge of 7.4 microcoulombs is separated from another particle with a charge of negative 3.6 microcoulombs by a distance of 1.4 meters. Find the direction and the magnitude of the force between the particles. List the givens. We have our two charges, a plus charge and a minus charge, and the distance between them. First, let's convert microcoulombs into coulombs. 7.4 microcoulombs is 7.4 times 10 to the minus 6 coulombs. Minus 3.6 microcoulombs minus 3.6 times 10 to the minus 6 coulombs. Use Coulomb's law to find the magnitude of the force. Don't include signs on the charges. We'll find the direction using a free body diagram on the next slide. So here's Coulomb's law. We substitute in the givens. Here's the Coulomb constant. Here are the two charges, and again, don't worry about the sign at this part, and make sure you square the distance in the denominator, and we get 0.12 newtons. We draw a quick free body diagram where Q is a positive charge and Q2 is a negative charge. They each exert a force on the other charge that is attractive. They want to move together. So the answer is the force between the two particles is attractive. A 1.4 nanocoulomb charge exerts a repulsive force of 20.0 millinewtons on a second charge which is located a distance of 2.2 meters away from it. What is the magnitude and sign of the second charge? We need to convert nanocoulombs to coulombs, and we're going to do that up here. 1 nanocoulomb is 10 to the minus 9th coulomb, and then millinewtons, a milli is 10 to the minus 3. So we now have our givens. Once again, we'll use Coulomb's law to find the magnitude of the charge, and then find the sign using a free body diagram on the next slide. Here's Coulomb's law, but we need to solve for Q2. Multiply both sides by r squared, and then divide by kq1, and you come up with this expression for Q2. We then just need to substitute in the givens, and we get 7.7 times 10 to the minus 3 coulombs. Since the force on the second charge is repulsive, right, it's moving it in that direction, it must have the same side as the first charge, that is, a positive sign. And Q2, of course, repels Q1. Two charges of 2.6 microcoulombs and minus 5.4 microcoulombs experience an attractive force of 6.5 millinewtons. What is the separation between the charges? We need to do a little unit conversion first. We have microcoulombs, and we turn that into coulombs by multiplying by 10 to the minus 6th. We do that for both charges, and then millinewtons is 10 to the minus 3 newtons. We start with Coulomb's law, but we have to solve it for r. So we multiply both sides by r squared, and then divide by the electric force, and then one more step, take the square root of both sides. We substitute in our givens, and be sure you take the square root after you do all the multiplication and division, and we get a distance of separation of 4.4 meters. Two spherical objects whose centers are 8 centimeters apart have equal negative charges and repel each other with a force of 9 millinewtons. What is the charge on each of them? How many extra electrons are on each of them? Start with unit conversion again. We have millinewtons, and we turn that into 10 to the minus 3 newtons, and centimeters into meters by moving the decimal place 2 places to the left. So let's use Coulomb's law to find the magnitude of the charges. This is a little tricky, but this happens a lot in physics problems. We have two equal things. So if Q1 is equal to Q2, we can say that both charges equal Q. We don't need a subscript anymore. So the product Q1, Q2 is replaced by Q squared, Q times Q. So here's our equation that we're going to use now. So we need to solve this equation for Q, multiply both sides by r squared, then divide both sides by k, and go ahead and put Q squared on the left. Then Q is the square root of force times r squared over k. Now, you don't have to do this, but this will save you an extra step in multiplying. Pull the r squared out, right? What's the square root of r squared? Well, just r. So our Q is going to be r times the square root of the force over k. We now substitute in our givens, and we get the charge on each one of these objects is 8 times 10 to the minus 8 coulombs. And see, if we didn't take the r squared out, we would have squared this term inside here, multiplied it by 9 times 10 to the minus 3. So that's an extra step. So you don't want to do that. So this is a handy way to show your equation. Let's assign a variable to the number of electrons on each charge. So we don't have to keep writing this. We say it's just n. We find that by dividing the charge q on the sphere by the electron charge, which is 1.6 times 10 to the minus 19th coulombs. So here we have n is equal to q over e. We found q on the last slide. Here's a charge on one electron. So the total number of excess electrons on each sphere is 5 times 10 to the 11th. And notice how the units cancel out nicely here, so we're just left with a number.